In this set of lecture notes, we're going to talk about applying Newton's laws, as well as going over some examples, particularly working on free body diagrams. So before we start that, let's remind ourselves what Newton's laws are. So first law talks about inertia and talks about how unbalanced forces change motion of the object. More specifically, it says that if there are no unbalanced forces acting on the object, then the motion of the object doesn't change, as in we say that acceleration is zero. We also know this law as equilibrium, or not so much the law as this statement here, sum of all forces is equal to zero. So that's known as equilibrium. We'll talk about that in just a minute. Second law is basically the same thing, but now it's kind of turned around, and it talks about what happens when the sum of all forces is not equal to zero. Basically, that means that acceleration is not equal to zero. Okay, so that's when we can figure out the cause and effect, right? So the net force is the cause, and the effect of that is acceleration. And finally, third law talks about action-reaction, that force that object 1 exerts on object 2 is equal and opposite to the force that object 2 exerts on object 1. So now we need to figure out how to apply those laws and how to draw free body diagrams. So let me elaborate a little bit on equilibrium. What we're studying right now is called mechanical equilibrium. Mechanical equilibrium, as opposed to something like thermal equilibrium, which at some point in time towards the end of the semester we'll also discuss. Or let's say in chemistry, you probably talked about chemical equilibrium. So there are a variety of different equilibria, and all of those obviously deal with different phenomena. So right now we're only sticking to mechanical equilibrium. There are two kinds. One is called static equilibrium, and the other one is called dynamic. So in general, mechanical equilibrium is expressed with this equation that I already wrote, but I'll write it one more time, that sum of all forces is equal to zero. Notice how it's a vector equation, right? So that's for either one of the two, static or dynamic. And of course, we just said that if sum of all forces is equal to zero, that means that acceleration is equal to zero, right? So that's true for both. Acceleration is equal to zero. The difference is that for static, velocity is also equal to zero, and for dynamic, velocity is not equal to zero. So if you remember, we wrote the statement of first law in words, and we said an object at rest remains at rest. So that's for static. And the object in motion remains in motion at a constant velocity. That's for dynamic. So I should write that too. Velocity is constant, not zero. Okay? Now notice that I wrote all of these equations as vector equations. So basically what that amounts to is that I should be able to break this up into the x component, the y component, and if it ever comes to that, the z component. Remember that one of the main principles of motion that we discussed was that x and y and z components are all treated separately and independently. We really haven't done anything with z, but that's beyond the point. So x, y, z are independent. And what that means is that you can have equilibrium separately in the x direction, or y direction, or z direction, or you can have some kind of combination of equilibria in multiple directions, or you can have no equilibrium in any direction. So just because you're saying that an object is in equilibrium in x direction, that means absolutely nothing about y, and vice versa. So keep that in mind as we're going over some of these problems. And speaking of problems, let me tell you a little bit about free body diagrams. Free body diagrams. A lot of times you will see people shorten that to FBD. Sometimes people even call them force diagrams, but I usually refer to them as FBDs. Okay, so basically a free body diagram is a way to represent all the forces acting on an object and the effect of those forces. And the effect of these forces. Okay, so let's see how that works. First of all, the word free here represents the fact that we isolate the object. We typically show an object as either a kind of a big dot or a box. That's entirely up to you. I think I tend to use the box a little bit more, but that means absolutely nothing. You can use either one of these notations. Okay, so it doesn't matter what the actual shape of the object is, at least not right now. Later, when we talk about torque, we'll bring that up and we'll modify that a little bit. But for the time being, the shape of the object, the size of the object does not matter. Okay, so let's write a list of rules that we use for a free body diagram. So that's actually number one. Isolate the object. So we're going to represent it as a dot or a box, right? And then we're going to show all the forces acting on this object. This is how I'm going to write it. Replace all contacts with forces. Now remember, in this class, at least in the majority of this class, we're talking about contact forces, right? Forces that occur as the result of a physical contact between the objects. And yes, I'll show you a couple of examples here. The only non-contact force that we have is force of gravity. So I'll make that number 3. So is there force of gravity? And the answer in 99% of cases is going to be yes. So the only situations where a force of gravity is not acting is an object doesn't have mass, which is very rare, unless the mass is so tiny that we can pretty much ignore it. Okay. And then another scenario would be an object is really far away from anything that can exert gravitational force, such as planets, stars, and so on. We have not talked about gravitation yet. That's coming up. Not today, though, so we'll get to that. Okay. And the third situation, which actually might come up, is if force of gravity is in the z direction or third direction, where all of the other forces that we care about are in the other two directions. So remember that all three dimensions are independent of each other. So sometimes, if you're only limiting yourself to one or two dimensions, force of gravity may not matter for those one or two dimensions. So in that case, you can ignore that. But in all other cases, you need to account for force of gravity. And of course, the way that we're drawing it right now, it's acting downward like this, right? Again, once we talk about gravitation and planetary motion and stuff like that, that's not necessarily going to be the case. But let's not worry about that just yet. Number 4, draw all the forces to scale as much as possible and label them. So for example, if you know that one of the forces is twice the strength of another one, draw it like that. Make sure that you're reflecting in your free body diagram the fact that one force is twice the other. Remember, the length of a vector represents its magnitude, so make sure you account for that. In some cases, in a lot of cases actually, you don't know that exactly. You don't know the exact magnitude of all the forces. But that's okay. Just try to kind of do your best and make an educated guess as to which force is bigger. Again, we'll see a few examples in a minute. Number 5. Velocity vector and acceleration vector are not forces. So if you want to indicate that an object is moving or accelerating or both, you can put velocity and acceleration vector on the free body diagram, but not on the diagram itself, but off to the side. For example, if I'm trying to create a free body diagram, this right here is wrong. Okay, so acceleration is not part of the diagram. So you can make a force like this as part of the diagram, and then somewhere off to the side you can draw acceleration vector. That's perfectly acceptable. But you cannot put acceleration and velocity as part of your diagram. And notice how I drew that force, right? So let me go back to number 2 for a second and just say that tail of force vector is at the object. Always the tail, that's how we draw these. And finally, number 6 is it should be clear from your FBD whether net force is equal to 0 or net force is not equal to 0. And again, keep in mind that that could differ or vary between x and y dimensions. So those are some basic rules that you follow in every free body diagram that you draw. Also, even if a problem does not state anything about drawing free body diagram, if there is anything mentioned in the problem about forces, you need to draw a free body diagram, especially if a problem is asking you to solve for a force, especially right now when we're dealing with mechanics. So some problems explicitly state, find, or rather draw a free body diagram, and some of them don't. But get this from the beginning, from the get-go, if a problem is about forces, there must be a free body diagram. No exceptions. Okay? Well, let's see how it works. I'm going to start by just discussing kind of an open-ended question. I'm not even going to ask you to calculate anything in this question. I just want to see if we can practice drawing a free body diagram. So an example is a person pushing a box along a level floor. Now, you can always draw a little schematic first. That is fine. There is absolutely nothing wrong with a schematic, right? But this is not a free body diagram by any means. A little schematic is just there to remind you of what is going on in the problem. You can represent all the contacts on this problem. You can draw the direction of motion. You can draw the shape of the object, whatever. It really doesn't matter. It can be something literally that simple as drawing a box and a stick figure, or just a couple of boxes. You really don't have to be an artist in order to be able to draw a schematic like this. Okay? So, notice how there is literally no information in this problem, and yet, just from that statement and from the little schematic, we can figure out what the free body diagram looks like. Okay? So, what's our object in question? The box. So we're going to draw a free body diagram for this box. What forces are acting on this box? Is force of gravity important? Of course. So let's draw that. Here is our force of gravity. We already know that for a fact. There is a floor, right? A surface. So you should also be able to conclude that there is a normal force, right? This box is not falling through the surface. It's supported by the surface. And notice how I drew those two, how I drew the force of gravity and the normal force. The movement of this box is horizontal. So there is nothing weird going on in the problem, right? The box is not jumping up and down. It's not flying off the floor. It's not falling through the floor. So there is absolutely no weirdness happening in the vertical direction. So as I'm drawing my free body diagram, I don't even know what else is going on. I haven't even put all of that on the free body diagram. But I can already scale those two forces to each other. I know there is nothing else that can possibly happen in the vertical direction, and that means that those two forces in the vertical direction are going to be balanced. So I'm drawing them the same magnitude. Okay? Then there is a push. Now, from the picture, the way that I drew it, obviously it looks like the push is coming from the left, but that's not how we draw a free body diagram. So we're going to draw this push force as originating with the tail of that vector at the object. And you can always call it F push or F person or F applied, however you want to call it. Just give it some descriptive name like this. Now, I kind of purposely drew this F push longer than the other two vectors. I really have no idea if that's the case. And it really does not matter. So I'm not necessarily scaling the x-axis to the y-axis. So that I have no information about, and it doesn't matter, right? Because I'm not trying to make any calculations. Now, if I did give you any numbers, you could go back and adjust the length of those vectors to be a little bit more representative of what's happening in the problem. But we're not doing that here. I'm not even asking you to do any calculations. So this is pretty much, however you want to draw it. The scaling in the y direction, that's essential because you're saying it's equilibrium in the y direction. The scaling in the x direction, we really have no idea. And did we take care of everything? Well, we replaced the surface, the floor, with the normal force. We took care of the force of gravity. We replaced the person with the force of push. So we took care of all the contacts. This problem also didn't say anything about friction. So let's just assume there is friction. Typically, usually it's a valid assumption. So force of friction is going to oppose or oppose the motion, be opposite of that force of push, right? So I'm going to draw it like this. Now, for this force of friction, we know that force of friction is defined as mu times the normal force, and mu is less than 1, right? So force of friction, I can say that that is lower than the normal force. The magnitude of it is lower. So I'm drawing that as a shorter vector. But that's all I can do here. I don't know from this problem if the box is accelerating or not. So I have no information to say anything about how force of friction and force of push relate to each other. So this is the best I can do for the time being, right? And again, what I'm using here is I'm saying I know for a fact that there is equilibrium in the y direction, but I don't know anything about the x direction, right? So the way that I've drawn it, I'm basically saying that the sum of all forces in the x direction is not equal 0. But that's only because I have no other information. Okay? So this is the best you can do in this particular problem, but you get an idea of all of these logical steps that are necessary in order to draw a free body diagram. Okay. Let's do another one. This time we will actually do calculations. Okay, another example. We have two boxes this time, a 2 kilogram box and a 5 kilogram box. They are in contact, and this applied force is pushing these boxes. Again, this is a schematic, so I can draw this force however I want. Horizontal applied force. And let's also say that this surface is frictionless. So if something is frictionless, you'll be told explicitly that it's frictionless. If it's not frictionless, then you should be able to infer that from the problem and to indicate the presence of force of friction. Okay, so here is my example. Let's say that this force here is 21 newtons. And the question would be to find acceleration of the system. Part A. There will be part B too in a minute. Okay. So, how do we do this? Well, obviously we need to draw a free body diagram. Remember, this is not a free body diagram. This is just a schematic. Also, notice how the statement of the question was to find acceleration of the system. So the whole point of a free body diagram is to isolate an object that we're working on. In this case, an object is the entire system. So system in general is defined as one or more objects that we're interested in. And those objects could interact with what's called the surroundings. So we can have a system, and then everywhere around it is surroundings. Or sometimes people also call that environment. Okay, so that's basically either it's the system that you're interested in or everything else, which we're going to call surroundings. So a lot of times external influences are going to come from the surroundings. So like forces, right? Forces come from the surroundings, from some kind of an external agent. Also, there could be other things. We'll talk about work later and heat. So those are also considered external influences. But let's not worry about them just yet. Okay? So going back to this idea. Here, the question is asking about acceleration of the system. So it means the entire system can be our object. Okay? So the way that I'm going to draw this is I'm not just going to pick one of the boxes, I'm going to pick the entire system. Okay? So what's the mass of the entire system? Well, that's easy, right? 7 kilograms. Now, sometimes you can draw, or rather label the mass, right, on the free body diagram. It's not a very common practice, but it might be helpful to do that, especially if you're going to be investigating different things. Or you can do this like by labeling the mass over to the side. I can say that I'm drawing here a free body diagram for the total mass. So that's up to you. I'm not going to require that you do one way or another, but especially if there are going to be multiple free body diagrams, multiple objects that are going to be investigated, make sure that you can read those free body diagrams and make sure you can communicate to me or to your classmates or to yourself what exactly each diagram represents. Okay, so what forces are present here? Well, obviously force of gravity, right? And obviously this is on the floor. Let me draw this a little bit more as a square here. Okay, so obviously this is on the level floor and it's not doing anything. So there is going to be a normal force. And notice how I'm adjusting it, right? Because I didn't really draw it quite as well the first time. So nothing is happening in the vertical direction. The applied force is horizontal. That means any kind of reaction, any kind of effect of that force is going to be horizontal. That should be self-explanatory to you. That if I'm pushing the box to the right, there is no way that that box is going to start jumping up and down of its own accord. It just doesn't happen. So use common sense, not just the physical picture, but also common sense. What could or could not be happening as the result of those forces? Okay? This system is frictionless, so I'm not going to worry about that, or the situation is frictionless. And let's see, what else am I forgetting? Oh, the applied force. Here is the applied force. That's it, right? We took care of everything that's in contact with the system, as in the applied force and the ground, and we took care of the force of gravity. So this is a fairly simple free body diagram. Okay, what do we have? Once we draw the free body diagram, always write a statement of either first law or second law, as appropriate. So remember, equilibrium can exist separately in the x direction or y direction, both or neither. So the statement of either equilibrium or absence of equilibrium, as in first law or second law, I can't speak. So that statement is absolutely mandatory. You will not get full credit on any exam if you don't write those statements. Notice how I wrote them, right? As vectors. So then the next thing is to figure out what forces contribute to each of those statements, to each of those laws. Now, we actually don't really care for y direction for this part of the problem, but let's do this anyway, because let you in on a little secret, there is the next part of the problem too. Well, anyway, let's practice. So, for most cases, we're using a standard coordinate system, right? X is horizontal, y is vertical, positive is up and to the right, negative is to the left and down. So, for the x direction, we only have one force, right? So that's all that contributes to sum of all forces in the x direction. So that's how I'm going to transition from Newton's second law to what's going on specifically in this problem. In the y direction, I have the normal force, which is positive because it's upward, and I have the force of gravity, which is negative because it's downward. And that's it, right? There is no other forces, so those two add up to 0. Okay. Right now, we have enough information to solve for acceleration. So I'm going to do this algebraically first. Right? Applied force divided by the mass. And it's always a good idea to indicate which mass you're talking about. So this is the total mass, right? The mass of the entire system. So let's make sure that we're careful with that. We know what applied force is, and we know the total mass of the system. Yes, I chose easy numbers on purpose. So acceleration here is 3 meters per second squared, and obviously it has to be to the right. So you can also go back to your free body diagram and say applied force is the only unbalanced force. That is very obvious from the free body diagram, right? So I know that acceleration is going to be to the right. I can draw that, not on the diagram itself, but a little bit off to the side. It's a great idea to do that because then you're kind of reminding yourself, oh yeah, that's what I'm solving for, right? That's what I'm interested in. So now we found this acceleration. Okay? We didn't really need the y component here, the y direction, but let's just see how far we can take that, just for practice. So we can move the force of gravity over to the other side, and then we can write force of gravity as total mass times g, right? So 7 kilograms times g, of course, is 9.8 meters per second squared. So I can calculate that to be so I can calculate this to be 68.6 newtons. Not that it's important in this problem, but why not? Okay, so that's it for part A. Part B, find contact forces. So what kind of contact do we have here? Only one contact, right? This surface right here between the two boxes. That's all we got. Now, if you look at the free body diagram that we already drew, we cannot see that contact on that diagram. And the reason is that the free body diagram only deals with external forces. Okay, let's go back to our description of free body diagram here. Okay, and then let's just make a clarification that these are external forces. Okay, so free body diagram only shows external forces, and that contact is internal to the system. So in order to be able to address the contact forces that happen along that surface, we have to break the system into two objects. So sometimes that's what you gotta do. You have to draw a separate free body diagram for each object. So I'm going to draw it for the 2 kilogram mass, okay, separately, and then separately for the 5 kilogram mass. Okay. All right. So what forces are acting on the 2 kilogram mass? Obviously the force of gravity. I'll call this Fg1. And there is also, I can kind of work them simultaneously. There is obviously also force of gravity for the bigger mass, Fg2. See how I'm scaling them to each other, right? So the 2 kilogram mass obviously has a smaller mass, so it's going to experience a smaller force of gravity. Okay? And the 5 kilogram mass is going to experience a larger force of gravity. They're still both on the surface, so there have to be normal forces. And still, doesn't matter if you talk about the single object or the whole system, there is nothing going on in the vertical direction. So I'm still going to scale those normal forces to balance out forces of gravity. Okay? And then, what else? Well, there is applied force, right? But that applied force is only applied to the 2 kilogram mass. So I'm going to draw that. I'm going to try to draw it the same exact length as in the previous free body diagram. Sometimes that works. Sometimes that's a nifty trick that you can use, that if you have multiple free body diagrams, kind of try to scale them to each other a little bit too. Okay? And finally, there is also this force. So if I'm numbering these objects 1 and 2, I'm going to label this force as F2 on 1. Okay? So object 2, box 2, is pushing backwards on object 1, right? Remember action-reaction? Okay, so that's how I'm going to label it. On every free body diagram, I'm only showing the forces external to that object. So I'm not going to do anything else, not going to do things like forces exerted by that object. That's not part of this diagram. forces only exerted on that object. And now my diagram is complete. That's it, right? I took care of all the contacts and the force of gravity. So if I go to my other diagram, the 5 kilogram one, the only other force that I need to draw is F1 on 2. And notice the way that I'm drawing this force is equal and opposite to this force. That's our Newton's third law. That's our action-reaction pair. So sometimes you'll also be asked to indicate the action-reaction pair. Okay? And notice how I'm also not drawing the applied force on box 2, because that applied force is not touching box 2. Now, the two boxes are in contact and they're accelerating together. We already calculated this acceleration, and I'm going to indicate that that's the same acceleration for both objects, because again, they're moving together, right? But notice how I'm drawing that acceleration off to the side, not as part of the diagram itself. Okay, so here are the two diagrams. Let's see what else we can do with them. This may be a little bit of an overkill for this particular problem, but because we're still learning how to work with free body diagrams, I'm going to go through all of the steps of setting up the solution. So I'm going to start by saying sum of all forces in the x direction is equal to mass times acceleration. Notice how I'm being very careful about which mass I'm considering, right? And then sum of all forces in the y direction is 0. We already talked about that. Okay. And then let's see what we can write for contribution of all of these forces into each of these statements. Okay, pay attention to minus signs. Okay, so that's for the x direction. You should be able to follow what I'm writing right now without me making any additional comments. So using standard coordinate plane, to the right is positive, to the left is negative. And same thing here. So we could calculate those normal forces individually. I'm not even worried about that right now. Right now, we're after the contact forces. The contact forces are highlighted on the free body diagrams. So look at the one on the right. I actually already have enough information to do that, right? We know the mass, and we already calculated acceleration. So I can do this calculation right away. Notice how this is a scalar, right? Already took care of the direction. So now when I plug all the numbers in, I'm just getting a scalar out of that. Okay. So that's done. Now I should be able to right away say that if F1 and 2 is 15 newtons, I should be able to say that F2 and 1 is also 15 newtons, right? Because those are action-reaction pair. Magnitudes are equal. Directions we already took care of. But in order to confirm that, let me also work out this equation on the left side. So you can use as many algebraic steps as you need to be able to solve for this. Okay, so if you need more steps in between, go for it. I'm going to substitute everything in. Guess I really didn't need parentheses there. Okay, so this is 2 kilograms times 3 meters per second squared, and I get also 15 newtons. Okay, so this makes sense that these two are equal and opposite, because they are pair, right? So yeah, we confirmed what we already said. So in some cases, you will have more ways than one to solve for something. Just make sure that you follow one of those paths. So here I had basically two ways of solving for F2 on 1. It's fine. I mean, whichever one works. Also, sometimes it's good to have that sanity check. So we got the two equal to each other. Great. That means we're doing this correctly. Okay. Let's see. Let's do one more thing here. Let's give it part C. So find net force on each mass. So we already know what the net force of the system is, right? That was just our applied force, everything else balanced out. But now let's figure out how to get the net force for each mass. We actually already sort of answered that question, except we didn't show it calculation-wise. So now let's do that. In the y direction, net force is equal to 0 for both masses, right? Because nothing is going on. The system, the boxes are not falling through the surface, jumping up and down, nothing of that sort. Okay, so we're good. Let's do sum of all forces. Remember, sum of all forces is the same thing as net force. So for the first object, it's going to be just m1 times a. So 2 kilograms times 3 meters per second squared, 6 newtons. That's the net force on m1. This is to the right. And for m2, net force in the x direction is m2a. This is 5 kilograms times 3 meters per second squared, which is 15 newtons, also to the right, like that. Okay, so remember that net force and sum of all forces is the same thing. Circle our answers. Okay, so those are some examples of you saw how to draw a free body diagram and how to write what's going on in that free body diagram in terms of equations.